All right. Ivy said something that, or she expressed something that I think several of you may have felt yesterday, and I felt the same way, even though I am teaching the class. I thought, gosh, that didn't make a whole lot of sense yesterday. So I've written myself some notes so I can just point and talk through it with you. These are on your 5.3 notes, so don't worry about writing them down. But let me try to do a better job of just explaining the basics of yesterday. First, we had the definition of area of a region in the plane. And in order for this to get this formula to give me the area of the region of the plane, in the plane, I had two conditions. I had that f had to be a continuous function, and it had to be non-negative, or its graph had to be above the x-axis on the interval, closed interval from A to B. Then the area of the region bounded by the graph, the x-axis, and the vertical lines x equals A and x equals B is given by this crazy looking formula that's a sum of a bunch of areas of rectangles. F of C sub I is the height of each rectangle, delta x is the width of each rectangle. When you multiply those, you get the area of each rectangle, and then this notation sums all of those areas up as the number of rectangles increases without bound. And then we got the definition of the definite integral, and like Ivy said, this is not exactly this. There's two differences between this notation and this notation. One of them is that this definite integral exists, and you can find it by what we're going to do today, whether f is non-negative or not. F still has to be continuous, but it doesn't have to be non-negative anymore in order to evaluate this integral. The other restriction that was removed is that this notation, remember, this is called a partition in X, and it's the width of the largest rectangle, and this is saying the width of the largest rectangle is going to 0. That if each rectangle is getting infinitely small, really that's the same thing as the number of rectangles increasing without bound. If the number of rectangles in a finite region goes infinitely many, then each rectangle's width has to be getting smaller and smaller. Now, what Ivy asked was, why are we removing the restriction that all of the rectangles have the same width? Like we had here, all of the rectangles had the width delta x. The best I can say to answer that, Ivy, is that these two statements are really equivalent to each other. If the number of rectangles is going to infinity, then the width of each rectangle is going to 0, and it doesn't matter if the rectangles are all the same width or not. Each rectangle's width is getting smaller and smaller and smaller. So we just kind of generalized it. Here we were saying if we have infinitely many rectangles of the same width, here we're saying it doesn't matter that all the rectangles have the same width. As the number of rectangles go to infinity, the width of each rectangle is going to be getting smaller and smaller. So it's a generalization more than a removing of a restriction. That's probably the best I can do with that question. Does that help a little bit, Ivy?
Yeah, that makes sense.
Okay, and then you said that was your first question, so what else did you want to ask?
I just didn't understand how integrals got involved.
I know, it's like, how the heck does taking a derivative to find an instantaneous rate of change relate to finding the area under a graph? You know, the definition of the derivative came from the average rate of change, but when you apply that limit notation to it when you don't just find f of b minus f of a over b minus a, but you take that and find the limit as b is getting closer to a, or the distance between b and a is getting infinitely small, then you're finding the instantaneous rate of change. That instantaneous rate of change undone will give you back the original function. Now, so far, does that make sense?
Yeah.
If I take a derivative and undo it, then I get back the original function. So here I'm undoing a derivative to get back an original function, and then I'm evaluating that original function. Oh, actually, I got ahead of myself. That's the fundamental theorem of calculus.
Oh.
Yeah, let's come back to that in just a minute. But we are given an original function. We differentiate it to have a formula for which gives us the instantaneous rate of change, and then we undo that and get back the original function. Now hold the other part of your question for just a minute. How do these two things relate? And other than you haven't gotten the answer to that question exactly yet, do you have anything else?
No, those are my two questions.
Okay, I love that you can articulate those so well. Sometimes you articulate the question better than I articulate the answer, but I think today's going to clarify some things. All right, so we have the definition of, oh, I'm sorry, does anybody else have a question? Let's see who joined us and I didn't say good morning to. Miss Abby, did I tell you good morning?
Yes.
Okay, Mr. Dillon, good morning.
Good morning.
And Mackenzie, good morning.
Good morning.
All right. So we have the definition of the area of a region in the plane, which is just adding up the sums of, or adding, that's repetitive, adding up the areas of infinitely many rectangles. And then we have the definition of the definite integral, which says, hey, this is what the definite integral means. This is the definition of the definite integral. Now, the thing is, yesterday, we had some pictures in our homework that had a graph and an area that's shaded, and we wrote the definite integral, which would give us that area. But the thing is, yesterday, we couldn't evaluate that definite integral unless this region ended up being some shape that we had a geometric formula for. This was a problem that we did as an example yesterday, and the only reason we could evaluate that definite integral is because when we graphed the function from 0 to 3 and shaded the region from x equals 0 to x equals 3 and bounded by the function and the x-axis, that happened to be a trapezoid. And we know how to find the area of a trapezoid. It's 1/2 the width times the average height. The average height from here to here would be 5. No, yeah, would be 5. Hey, you know what? I just wrote that this morning, and that's what it's supposed to be. Just the width times the average height. The width is 3, the average height is 5, and so we know the area is 15, and that means the definite integral is 15. But again, the only reason we could do that is because this is a shape we recognized. So the big question for today is, how could we have evaluated that definite integral if that hadn't turned out to be some geometric shape that I had a formula for? And the answer to that question definitely deserves a drum roll. And I'm waiting. And I still don't hear drums. All right, that is the fundamental theorem of calculus. Just the name of that gives me chill bumps. This is what Ivy's been waiting for her whole life. And it's pretty simple. The fundamental theorem of calculus says, it tells us how to evaluate this definite integral if it's not it doesn't form some region that is a shape that we have a formula for. And the fundamental theorem of calculus says, if a function f is continuous on a closed interval. Now notice it didn't say continuous and non-negative. We could have a function that, as I said yesterday, we could have a function that is some below the x-axis and some below the y-axis. And we could still evaluate that definite integral, even though if we did evaluate it, it wouldn't be the area of, wouldn't be this area, because from here to here would give me a positive value. Integrating from here to here would give me a negative value. And so if I just evaluated the integral from here to here, then the value of that integral would be 0. This area would cancel out that area. So we can evaluate a definite integral, but it doesn't necessarily represent area unless the function's non-negative. And we'll come back to that in a second. But if a function is continuous on a closed interval from a to b, and f is an antiderivative of the function on the interval from a to b. Now remember, if the function f is a derivative and we integrate it, we find the antiderivative. That's a whole family of antiderivatives. When we found the antiderivative for let's see, 3x squared, the derivative for 3x, antiderivative for 3x squared was x cubed plus a constant, and that constant could have been anything. So if f is one of the antiderivatives, and all the antiderivatives only differ by a constant, +7 or -6 or plus pi wouldn't affect the value of the antiderivative. If f is an antiderivative of little f on the interval from a to b, then we can evaluate this thing that we had not been able to evaluate before by substituting b into the antiderivative, then substituting a into the antiderivative, and subtracting the antiderivative evaluated at b minus the antiderivative evaluated at a. All right. I heard no gasps, and I understand why. It's like, what the heck? This is going back to what Ivy said a minute ago. What does this have to do with derivatives and antiderivatives? Well, if you have a function f and you take its derivative, now let's say the capital F's and lowercase f's are confusing here. Let's say we have a function f, capital F of x, and we take its derivative, and it gives us, that doesn't look much like a capital F. We take its derivative, and it gives us some little f of x. And then we integrate that little f of x. It gives us back the big f of x. So here's differentiating, and here's anti-differentiating. This derivative gave us the a formula for finding the instantaneous rate of change, or the function f of x. It's like the slope formula using capital F of x. When we integrate that, we're getting back the function whose derivative gave us, this is hard to say. We're getting back the original function. It's going in a circle here. This was the instantaneous rate of change. This was getting back the original function, capital F of X. Let me put from A to B on here. Evaluating the original function at B and evaluating the original function at A, and then subtracting those two values. Ivy, that still wasn't great. Instantaneous rate of change. Let me prove to you that it works. And I just need to do a better job of explaining why it works. It's always easier to show that something works in one problem than to explain why it works for all problems. But if we go back to this number 32 and we say, we already know the value of this is 15. We just want to show that the fundamental theorem of calculus will give us the same thing. Help me find the antiderivative of 8 minus 2x. What's the antiderivative of 8, or the function whose derivative is 8? The function that if you take its derivative, you just get an 8.
8x.
Yeah, 8x. And what's the function that if you took its derivative, you would get a 2x?
X squared.
Okay, and let's just double check that. Is the derivative of 8x just 8? Yes. Is the derivative of x squared just 2x? Yes. And then if we wanted the whole family of antiderivatives, if that upper and lower bounds weren't there, we would say plus a constant. Now I'm going to stop writing that in just a minute and you'll see why, but I've got a new symbol for you. This vertical line means evaluate that antiderivative from x equals 0 to x equals 3. And it's going to look just a little bit different in the next problem, because I'm going to explain to you why you don't have to write this constant, and then I'm just going to write vertical line with 0 at the bottom and 3 at the top, but that means x equals 0 to x equals 3. All right, let's evaluate this definite integral, or excuse me, evaluate this antiderivative at 3. Put 3 in the place of both x's. You would have 8 times 3 minus 3 squared plus a constant that we don't know. And then put 0 into the antiderivative. This is the fundamental theorem of calculus. Find the antiderivative evaluated at 3 and subtract from that the value of the antiderivative evaluated at 0. We would have 24 minus 9 plus some constant we don't know, and it really doesn't matter, it could be anything, minus 0 minus that same constant. What's 15 plus a constant minus a constant?
$15.
It's just 15. The same thing that we got by using the area of a trapezoid formula. to evaluate that definite integral. Now, the reason we're not going to write this plus a constant anymore is you can see that if you evaluate the antiderivative at 3 and then evaluate it at 0 and then subtract, you're always going to have a plus c minus c that cancel each other out. And so we don't put that constant in when we're evaluating the antiderivative. Actually, we're not going to put it right here. We're just going to say evaluate 8x minus x squared at 3 and at 0, and then subtract. Let's see, Miss Grace is joining us. All right, so Ivy, that does not explain why, or it doesn't explain what the derivative and antiderivative have to do with each other and how finding the instantaneous rate of change relates to finding the area under the curve. But it does prove that the fundamental theorem of calculus worked on this problem. Finding the antiderivative, evaluating it at the upper limit, evaluating it at the lower limit, and then subtracting gave us the same thing that we got when we used that formula. And let me think one more second. Something was coming to mind here. If this is the derivative that we're anti-differentiating, this is the instantaneous, I'm saying instantaneous rate of change, but really I should be saying a formula for finding the instantaneous rate of change at any given value of x. Ooh, I just thought of something that might help. What did we say if we have the position function? Yeah, this is going to help some. If we call it s of t, then what do we get when we take the derivative of s of t?
Velocity.
That gives us the velocity function. All right, and again, integrate the position function, and that gives us the velocity function. So when we undifferentiate or anti-differentiate the velocity function, what should it give us? If we undo, if we anti-differentiate the velocity function, really, I didn't mean, yeah, I didn't mean to make that brace include the integral, integrand, no, integral sign. If we integrate the velocity function, we should get back the position function. I'm not through, but so far so good?
Yeah.
Okay. If we attach the limits a and b to that, and we use the fundamental theorem of calculus to evaluate this from a to b, in other words, if we find s of b minus s of a, what would that really give us? I'm talking words. If I said this is the position function and I'm evaluating it at B and evaluating it at A, and then subtracting those.
The change in position.
That's awesome. Good job, Ivy. That's a change in position because we're substituting those numbers into the position function from x equals B to x equals A. So another interpretation of the definite integral, we've been talking about the interpretation of the definite integral as being area, as long as we're talking about an interval over which the function is positive. But another interpretation of the definite integral is called total displacement. It's just how far, if you know how fast something's moving, and then you integrate it to find the position function, and you evaluate the position function at the lower limit minus, or the upper limit minus the lower limit, you're finding how far the thing has moved. Ivy, it's easier to explain the displacement interpretation of the definite integral than it is to explain the area interpretation of the definite integral, because this is linear, this is one-dimensional, and the area interpretation is two-dimensional.
Okay.
That helped me a little bit. Did it help you a little bit?
Yeah, I definitely understand it a bit more now. I'm still having trouble placing it now to area.
I'm gonna say that I am too. That's something that I need to, I need to be able to articulate better. But it's not gonna come to me right this minute. When I try to pull something like that out of the air, we end up just sitting in silence for a while. We don't have time to do that. I am going to think hard about that, Ivy, and I'm going to send an email that articulates why a definite integral can be interpreted as area. Not just why a definite integral can be articulated as displacement or interpreted as displacement, but why it can also be interpreted as area. And that's the question you're asking, right, Ivy?
Yeah.
Okay, I'm going to put that in words and send all of you an email later. But let's go to today's notes. Actually, I don't see any point in doing 1, 2, 3, 4, 5, 6 of these. If you can find the antiderivative and you know the fundamental theorem of calculus, then it is not difficult to evaluate any of these antiderivatives. Maybe let's just do these two that aren't just algebraic, like examples 1 and 2 are. Number 28, and by the way, I'm going to show you how to evaluate a definite integral on the calculator. And if we were taking a paper test in class, you could evaluate all the definite integrals on the calculator and just give me a decimal approximation, or you can hit the fraction button on your calculator that changes this decimal approximation back to an exact answer. But there's no point in me giving one of those on the test because it's just a calculator problem at this point. So on the test, you only have a couple of definite integrals that say give the exact answer, and they're going to be trig, because that's the only one you can't just punch on your calculator and find the answer without understanding anything about a definite integral. So there'll be one like number 28 or maybe like number 32 that you'll actually have to know the fundamental theorem of calculus to evaluate. So number 28, I want the antiderivative of 2 minus cosecant squared x. I want the function whose derivative is 2. What is that?
X squared.
Nope.
Oh.
The function that if I take its derivative, it just gives me 2.
Oh, 2x.
2x, right. Now you may have to go back and do some problems from 5.1 just to practice finding antiderivatives. But I've got to squint really hard and remember which one of my trig functions that if I anti-differentiated it, oh, I said that wrong. If I differentiated it, I would get cosecant squared. Which one of my trig functions has as its derivative cosecant squared?
Cotangent?
The derivative of tangent is secant squared. The derivative of cotangent is cosecant squared, except for I need to think, what would give me this middle term being negative? The derivative of cotangent, is it positive cosecant squared or negative cosecant squared?
Negative cosecant squared.
Yeah, all those co-functions had a negative derivative. So I'm gonna write down the cotangent x, and I think that's supposed to be negative. But the beautiful thing about anti-differentiating is you can always check it. If you take the derivative of 2x, you do get 2. If you take the derivative, ooh, I'm glad we're checking this. If you take the derivative of negative cotangent, you would get positive cosecant squared. So that's not right. We're just checking our answers, just like we did with factoring when we first learned it. That would have to be a positive cotangent x in order to differentiate and give us back negative cosecant squared, because that's the derivative of a positive cotangent is negative cosecant squared. All right, so far so good. We anti-differentiated, we checked it to make sure we hadn't made a mistake. If this was a indefinite integral, if those limits weren't there, I'd just have a plus c and I'd be through. But I'm evaluating a definite integral, so I don't need the plus c. The plus c and the minus c would cancel each other out anyway. I just need to evaluate that antiderivative at pi over 4 and pi over 2. Make sure you substitute the upper limit first and subtract from that what you get when you subtract the lower limit. So that would be 2 times pi over 2 plus cotangent of pi over 2. Make sure you use parentheses for that. Minus what you get when you plug pi over 4 into the antiderivative. 2 times pi over 4 plus cotangent of pi over 4. All right, 2 times pi over 2 is just pi. What's cotangent of pi over 2? Here's the mental image that should pop in your head. Pi over 2 is that point on the unit circle that coincides with the positive x-axis. The ordered pair there is 0, 1. So what is cotangent?
0.
Cotangent is the y divided by the x. Cotangent's the x divided by the y. So 0 divided by 1 is 0. That first expression turns out just to be pi. Minus 2 times pi over 4, keeping up with my parentheses, is pi over 2. What is cotangent of pi over 4?
1.
Yeah, pi over 4 is that first quadrant angle where the x and the y are both square root of 2 over 2. So that divided by itself is 1. And cleaning that up as much as possible, I would have pi minus a half pi is a half pi. And 0 minus 1 is negative 1. The reason I'll give you a problem similar to this, I think maybe 2 problems similar to this on the test, is because you have to know the fundamental theorem of calculus. Your calculator won't give you that exact answer. And that's what the test asks for. If you just punch that on the calculator and get a decimal approximation, it's 100% wrong because the directions say find the exact value. All right. Let me see. Another thing I meant to do before I got with you this morning. I'm trying to see if I remember how to do this on the TI-84. Not the way that I've typed for you down here. This is one way to evaluate that definite integral. But I'm thinking I want to show you another way to find it. If I just enter the function 2 minus cosecant squared as a function that I'm going to graph, 2 minus, how do I enter cosecant squared? I don't have a cosecant button. We've been doing calculus so long, we've forgotten trick.
1 over sine squared.
Yeah. 1 over sine squared. Oops, see, that won't be right. Try that again. 2 minus 1, let me use parentheses, 1 over sine x. Close that parenthesis, close my other parenthesis, and then square it. What I'm showing you would be cosecant squared. If I just graph that function, and I have no idea what my window is set to, so I'm going to go back and set it to standard zoom and 6. That's what cosecant squared is going to look like. That series of parabolas, normally you would have one up, one down, but if you squared them all, then they'd all be concave down like that. Let me change my window, since I'm going to evaluate that from pi over 4 to pi over 2, and I want you to be able to see that really well. I'm going to change my window to be counting from 0 to pi by quarter pies. Zero to pi by quarter pies. And my y's, I don't really care what they are. Let me graph it again. All right. So from 0 to pi over 2 is that little piece of the graph that's above the x-axis. Now that I can see it better, I'm going to do one more bit of tweaking on my window, and then I'm going to show you how we can get this pi over 2 minus 1, how we can get a decimal approximation of it. Let's just make my y's be from -2 to +2. Because I really just want to see that part that's above the x-axis. At this point, it's hard to tell it's not a parabola. All right, coolest thing ever. Coolest thing ever, if I remember where it is on my calculator. Second and calc, and number 7 is the integral sign, the indefinite integral of f of x dx. When I enter a 7, it's going to ask me for the lower limit, which is supposed to be pi over 4. Then it's going to ask me for the upper limit, pi over 2. Watch what happens when I enter that. That's the area we just found, from pi over 4 to pi over 2. Your calculator shades in the area that that represents. Now, the only reason that this pi over 2 minus 1 represents the area under this curve is because from pi over 4 to pi over 2, that graph is continuous and non-negative. If we wanted to evaluate it from 0 to pi over 2, we could get an answer to that, but it wouldn't be an area because from 0 to pi over 4, the function's below the x-axis. All right, do you like seeing that?
I think if I do a bit of those at home and look at what you said, it might make more sense.
That's usually the case in any math class. In class, you just try to get it all copied down, and then you go home and you have to think really hard to make it make sense. Some folks just think really hard to get the right answer and don't care if it makes sense, but y'all are beyond that, I think. You need it to make sense so that Calculus 2 will make sense. Hey, one other thing, this decimal approximation's about 0.57. Well, let's check that with pi over 2 minus 1. Pi over 2 minus 1 is the same thing. All right, that's the fundamental theorem of calculus. Like I said, this is a different way to evaluate. Well, let me just show you. Let's do the same problem, but do it this way without graphing. It's math and then number 9. You can't see number 9 until you scroll down, but you don't have to see it. If you know that FNINT is number 9, you can just enter a 9. And look how that looks on my calculator. That's exactly what the original problem looked like. I can say integrate from pi over 4 to pi over 2. The function is 2 minus, I'm going to have 1 over sine x in parentheses. And because my calculator opened a parenthesis before the x, I had to close that parenthesis and then close the parenthesis I opened, and then square that, and then close this last parenthesis. And the last thing showing is my variable of integration is x. Same answer. So you can get a decimal approximation of that answer to check your answer on the test. Your answer on the test is checkable. You should not miss this problem. You've got to do it by the fundamental theorem of calculus to get the exact answer, but then you can check your exact answer with a decimal approximation by either the graphing method that I showed you or this FNINT. Now, these other examples, just practice using parentheses. because you do want to check your answer on the test. And so you need to practice using this to make sure you have all your parentheses opened and closed in the right place. I had to be really careful with parentheses here. As soon as I pull up FNINT, my calculator opened that parentheses, but I had to say 1 over sine x in parentheses, and then hit my square button to square that whole thing, and then close another parenthesis. Actually, I believe, oh, I know what it was. When I hit sine, my calculator opens a parenthesis right there. I have to close it. I had to have this whole big thing in parentheses. So just practice checking your answers. Tonight in the homework, when you get an exact answer, check it on your calculator and make sure that you can do that on the test. All right. Don't worry about being able to type that on the calculator. If we were in class, if we had plenty of time, we would talk about how to enter. Actually, to do this by hand, by the fundamental theorem of calculus, you'd have to understand all this, but to evaluate that on the calculator, let me show you where your absolute value is. If I say math 9 and evaluate that integral from 0 to snap. From 0 to 4, absolute value is under math also. I can say math and then it's under number. Number 1 says absolute value, and I could keep typing the function. I got that absolute value in there now. But don't worry, I wouldn't give that to you on the test. You haven't had enough time to practice it. All right, we're almost out of time. Let's see. Number 3 is just enter that on your calculator exactly the way I've typed it. Make sure you can get that answer. And then there's a problem on the test that says determine the area of the indicated region. Well, in last night's homework, you had some problems that said write a definite integral that would give you that area. Now you know how to evaluate that definite integral without having to have some shape that you have a formula for in geometry. Geometry doesn't give us a shape for finding the area of something that has a curve in it. So what definite integral would give us that area? I'd integrate from what? Your bounds of integration are your vertical lines on the left and the right that bound that region. So you would integrate from 1 to 2, the function with respect to x. If I just say find the area and I don't say exact value, then you can punch that on the calculator. If I said find the exact value, then well, actually for algebraic functions, your calculator would still give you an exact value. But if you didn't have a calculator, you could evaluate that by the fundamental theorem of calculus. Number 38 is where I typed out how to graph it and find the definite integral. So number 38, what integral would give me that area? Integral from what to what?
Pi over 2 to pi.
Well, I'm integrating from the y-axis all the way to pi. What you said, Ivy, would be if my shading stopped here on the left, but it goes all the way to the y-axis. So I'm integrating from 0 to pi, the function with respect to x.
Yeah, I don't know what I was saying.
It's okay. All right. I'm just going to tell you this in 30 seconds or less. This is the last thing. I want you to read that. I think it'll make sense. The last thing I want to say, you know what? It's okay. Tomorrow, we're just doing questions from the practice test, and that could either be these problems or the problems that I've listed from the review, or the practice test that I've put in my math lab. So before we get into those questions from practice test tomorrow, we'll talk about these last two things. I don't want to rush them. They're pretty easy, but I want a minute to talk about them. So don't worry about the average value and the word problem in the homework for tonight. Okie doke?
Okie doke.
All right. I'll see you tomorrow. Do the practice test so that you can ask me good questions. Don't just come in and go, I don't remember how to start this. Look in your notes for how to start it. Ask me questions on anything you've tried and you couldn't get the answer. All right. Y'all have a great day. Email me this evening if you need to.
I have a quick
Yes.
question, just because I'm
Yes,
in
ma'am.
So when we were writing the top and the bottom number on the integral sign,
Mm-hmm.
if we're just taking an indefinite integral, could you write negative infinity to positive infinity? Or,
Well, think about, let me think about what you just said. Let's take the sine function from negative infinity to infinity, would look like this. We could do a better job, but look like that. If you evaluated that, are you saying you want to find the value of the definite integral from negative infinity to infinity? Is that what you're saying?
no, I'm just saying if we're taking like the indefinite integral, would it be correct notation to do that? Like even
Oh, no. Just like a derivative is a function and antiderivative is a function, the value of a definite integral is not a function, it's a number. Now, this is actually something called, something we're going to talk about in Calculus 2. Indeterminate integrals, either your upper bound or your lower bound or both, are not just numbers. They're negative infinity to infinity, perhaps, or 0 to infinity. Those are called integrals of indeterminate form, and that's Calculus 2. But that's not the same as the antiderivative. This would yield a number, and if it's defined, and the antiderivative is not a number, it's a function.
Oh, okay.
All righty, let me get with my pre-calculus folks. Y'all email me. Look for an email from me later today. I'm going to give you a better explanation of why the definite integral, why antiderivatives have anything to do with area. Ivy's #1 question from yesterday.
Okay.
All right, y'all have a good day.
Bye.
Bye-bye.